our goal today is proving another formula which will be similar in spirit to the law of sines. So maybe it's good to even start by recalling the law of sines. And let's do it this way. I'll use the same letters, so this will appear down here. C, B, little b, little a, big A. So what does the law of sines say about that right triangle? Not a right triangle. Sorry, you're eating that triangle.
Yeah.
I want the right triangle that I just do it. Cool. So you can use that as soon as you're given enough information, well, some information to perform a pair of opposites. Once you know a pair of opposites, you're in a situation where you can try to use the law of sines to deduce some stuff. So I'm going to go for another sort of rule. So if you like, that's playing a game an awful lot like SOHCAHTOA, but if you don't start with a right triangle. It tells you what sine tells you what angle. What I'll aim for today is something that will feel like the Pythagorean theorem, except where you don't start with a right triangle. And so as you said, if you think about this right triangle, you get the fact that c squared is the same thing as a squared plus b squared, which means if you know, well, if you know any two sides of a right triangle, you can figure out the plot by solving that equation for whichever side length you need. Let's try to do the same, but where this angle theta isn't a right angle. And so I guess that means that if you take that angle and you shrink it, it looks like the side length c will get smaller. If you take that angle and embiggen it, the side length c will get bigger. So that angle c will somehow determine that what this angle is instead of a right angle will determine what the side length c is. Now let's try to figure out how. So let's try to walk it out this way, and let's do it by, we're really good at doing stuff with the right triangles. So let's break this triangle up into two different right triangles by dropping an altitude, finding the height of it. So our goal is determining the side length c in terms of a and b and this angle theta. Well, so let's see. Let's start with this. Maybe let's just have a sketch of it. If I knew what h and a1 were on that picture, can I figure out what c is? Yeah, it would be the sum of the squares. So if I could figure out these two side lengths, I'd be happy. Well, let's look at this right triangle now. I'm allowed to use theta and I'm allowed to use b. Is that enough information to determine what h is? I think so. Is it enough information to determine what a0 is? You could use SOHCAHTOA. So, cool, what does that mean? That means out of theta I could figure out h, out of theta and b I could figure out a0, but a0 plus a1 should be all of a. So I can figure out a1, but then h squared plus a1 squared is c squared. So there's a plan of attack. Let's just follow that plan and see what formula it leads us to. So let's take a look at this leftmost right triangle. That's a good first step. What trig function would you want to use to figure out h in terms of b and theta?
Law of sines? Or no?
Not even the law of sines, just like the
okay.
part of SOHCAHTOA.
Okay.
Which I guess is secretly the law of sines, but the sine of a right angle is 1. So one of the things you would divide by would just be 1. But let's not use the fanciest tool. Let's use the simplest tool we can. So determine h in terms of theta and b. The sine of theta is opposite the height divided by the hypotenuse, which is b. So it looks like h is equal to b times the sine of theta.
So we know what h is.
Same thing. Let's figure out what a0 is. What trig function seems useful to find a0?
Cosine.
Cosine. Because cosine of theta will be adjacent over hypotenuse. Oh, that's a B.
Okay. Cool. This side length plus that side length is the big side length. So, could you use that to determine what a1 is? Oh yeah, I guess you would just subtract, right?
So a1 is a minus a0. So I now know a1. And let's maybe even let's evaluate more. So that's a minus, I know what a0 is, it's b multiplied by the cosine of theta.
Everyone with me so far? So I now know h and I know a1. Since that's the right triangle, can I just use the Pythagorean identity to find c? Of course I can.
So c squared is exactly equal to h squared plus a1 squared.
But of course, I don't want a formula in terms of h into a1. I don't want to need to find h and a1 to find c. So I want to expand out the fact that I know those to see what the formula becomes. What is h?
B times the sine of theta.
B sine theta. So h squared is the square of that.
So let's see, I'll try to color code some. So that h squared is b squared sine squared theta.
Do I have a formula for a1? Sure, it's the thing that's right above.
Plus a minus b cosine theta, quantity squared.
So you can't really tell that that was green, but you can tell the difference between green and blue, right? Okay. And I guess that's even bordering into the territory of theta b. So in some sense, there's a formula for c squared in terms of a, b, and theta. Now, I want a formula that I can actually use. So it would be best to simplify this as much as possible. Let's try to simplify that. And maybe we'll start by FOILing this out, seeing what it becomes.
So, what will we wind up with? C squared is b squared sine squared theta plus, and now, let's see, I need to FOIL that out. So I'm not going to get a squared minus b squared cosine squared theta. That's not how multiplication works. You have to FOIL it out. You'll get a squared minus 2ab cosine theta plus b squared cosine squared theta.
Everyone with me right now? Right, so all I did is I not factor, the opposite of factor, distributed. So let's see, do you see any, so that gives me another formula, but you should do as much to simplify as possible. Does anyone see two things that should simplify when considered together? Yeah.
2b squared sine squared theta.
Something like those two?
Yep.
In fact, maybe I'll even correct you a little bit. One of them is a sine squared, the other one's a cosine squared. So actually we get something better than just 2 times b squared cosine sine squared theta. Let's take these two pieces. Right, you could imagine writing those, rewriting it so those two are next to each other and then factoring out the b squared. So imagine doing that in your head. You would get b squared sine squared theta plus cosine squared theta plus a squared minus 2ab cosine theta. Oh, parentheses matter. What's sine squared plus cosine squared?
1.
Yeah. Oh, yeah. So I like the reminder that I'm still recording because maybe that'll stop me from, like, at the end of class taking out the memory card without stopping recording, which destroys the file. It's annoyingly placed, though, isn't it? Anywhere would be annoyingly placed. So, sine squared plus cosine squared theta is. Thank you for understanding that, even though the terrible slaw in that speech. B squared plus a squared minus 2ab cosine theta. And now let's just take a look. Is that formula simpler than the one we started with? Yeah. I guess the only other thing you would want to do is, it's weird to write b before a. It should be an alphabetical order. So, the law of cosines says that if you have any triangle with side lengths a, b, and c, and theta is the angle that's opposite the side C, or equivalently the angle that's between A and B, then C squared is the same thing as A squared plus B squared, the Pythagorean identity, but it can't possibly be the Pythagorean identity. The angle theta isn't a right angle. You are off by 2 times A times B times the cosine of theta. How do people feel about that formula? So I went through the walk of deriving the formula, but the main point of this lecture is know that formula. That formula is a useful formula. Yep, let's use it to do some things. So, rewriting again for the sake of reference. If you have a triangle with side lengths A and B meeting at an angle theta, and you would like to know the side length C, then you can get the side length C via the formula C squared is equal to A squared plus B squared minus 2ab cosine theta. How many people think I'll probably wind up putting a question which involves the law of cosines on that exam I'm going to give at the end of this week? Yeah, so you should maybe put that formula on your note sheet and know how to use it. Let's use it. Let's compute the side length C given this information. You have a triangle with sides 3 and 5, meeting at an angle of pi over 3. You would like to know the side length C. And many of you are already putting pencil to paper. That's good. I'll start going through it. So the Pythagorean identity says that, nope, not the Pythagorean identity, the law of cosines says that C squared should be the same thing as 3 squared plus 5 squared minus 2 times 5 times 3 times the cosine of pi over 3. And let's go through the law. Let's just start reducing this down. I mean, a bunch of you are already pulling out calculators. So how many people actually want to go through the arithmetic slowly while I'm just writing down what that number is? What is that number? On the right-hand side.
It's 26.5.
Everyone getting 26.5? People getting other things? I think that it should be a whole number. So,
15.
I hear a 15.
I think that's enough controversy, but let's actually try to compute it. 3 squared is 9 plus 25 minus 2 times 5 times 3 is 15 times what's the cosine of pi over 30? So I suspect that you left out this first 2.
Yeah.
So we'll wind up with 9 plus 25 minus 15. Is that 19?
Yep.
Okay. So I mean, this is a reason. So if you go straight to just plugging things into a calculator, I don't know if you guys did. Be careful to double check what you plug in. It's worth doing some simplifications in your head before you start typing it in, because it's probably easier to know that 3 squared is 9 than is it to plug in 3 squared into a calculator. So c squared is 19. So what is c? Nice. Cool. Everyone feel pretty good about that? So somehow that tells you if you see a side and the side of a triangle and know the angle between, that's enough to know what the whole triangle is. At the very least, it's enough to know what the side opposite is. Let's think about one next example. Suppose I tell you all 3 sides of a triangle and ask you to say, discover the angles. Let's not actually do it, but let's kind of go far enough that you can see that you could do it in this little mini example. So let's just see what the law of cosines tells you. And we're going to use the law of cosines centered at one of the angles, A or B or C. And people would rather use the law of cosines centered at A. Centered at B? Centered at C? Okay. The B's have it. I guess you just wanted the picture that looks the most like the picture above. It wouldn't matter which one you picked. So let's use the law of cosines to achieve something. Let's try to figure out the measure of this angle B. So let's use the law of cosines. Law of cosines tells you that 3 squared is the same as 4 squared plus 2 squared minus 2 times 4 times 2 times the cosine of little b. Let's see, do you think you could take that and solve it for the cosine of little b? And I'm not saying do it. There's not enough space to go through the walk right here. So solve for little b. So you'll get something like cosine of little b is equal to some stuff. Once you have an equation that looks like cosine of b is equal to some stuff, how can you write down what b is? How about inverse cosine? Right, that's the whole point of inverse trig functions, to solve equations that look like cosine is equal to thing. So, whenever you see all 3 sides of a triangle, you can solve for any of the angles. How many people are concerned that there might be more solutions than just that? I mean, it's a reasonable concern to have. Generally, if you say cosine of b is equal to a number, you get infinitely many solutions. But what numbers are you allowed to see as angles inside of a triangle?
Positive things.
Positive. And what's the biggest angle you could possibly see?
179-ish.
Yeah, almost 180. So the only angles you're allowed to see are between 0 and pi. And maybe you can't actually see an angle of 0. Cosine from 0 to pi looks something like that. How many solutions does cosine is equal to a number have in that interval? 1. So there's no worry about multiple solutions. Whenever you see a side-side angle triangle, side-side angle, time constraints say maybe I won't do this until I get to the end. But let's talk through it in minimal detail. So this is a situation where there's possibly multiple solutions. So this is like an ambiguous problem. But it's not that ambiguous. There are at most two solutions. There might be zero, in fact. Do you know a pair consisting of an angle and a side opposite? Yeah. You see pi over 3, and you see 30. And you also know this side length, too. So you can use the law of sines to get that angle little a. Once you know little a, how can you figure out little c? What do the angles of a triangle have to add up to? Pi 180 degrees. I'll stick in radians because I'm going to stick in radians for now. Because that's in radians. You can say c is equal to pi minus pi over 3 minus a, which you know. And I guess the only thing left is to figure out the side length a. Do you know the angle opposite a? So you can use the law of sines again to get a. And maybe I'll put a little asterisk right here. There might be two solutions even in that false step. That's just a recollection from last time. Everyone feel okay? Let's go through some more. Let's suppose I give you a side angle side triangle. Like that one. Do you think you could take that triangle and figure out the side length C? Yeah, of course you can. In fact, we did that above. Law of cosines lets you get the side length C. But now you know all three sides of that triangle. Is that just a previous one of these lines? Yeah, it is. It's this case. You know all three sides, so you can figure out all of the angles. You happen to already know one of the angles. Use item 1 above to get little a and little c. Yeah.
Could you also use law of sines to get the other angles?
Yeah, that's actually just as easy. And one last one. Let's suppose I give you two angles of a triangle and one side. What's the approach you could use for this one? Let's see. At this point, do you know an angle and a side opposite to use?
I don't think we figured it out.
Yeah. So, I mean, either yes or no would have been a correct answer to that question. You can find A by taking pi minus the other two angles. 180 degrees minus the other two angles if you happen to be walking in degrees. At that point, will you have an angle and a side opposite? So you're set up to use law of sines. Does that seem pretty okay? So those are the various strategies you can use to solve triangle problems. If I give you three quantities on a triangle, generically you can figure out exactly what the triangle is. Some exceptions. Let's use this in practice to solve some problems. So first let's do one that's reasonably explicit if abstract. Here is a triangle where I've given you three of the side lengths. It's not drawn to scale in any sense. The side length 6 should probably be the biggest side length, but it's not in the picture. Let's try to figure out what each of the angles is.
And I think the way that I'll want to do this is I'll go through the walk of figuring out the cosine of A and then figuring out what the angle A is. And you guys will figure out the remaining two side lengths. I'll separate you into groups and you'll do them that way. So let's start. So let's use the law of cosines to figure out what
this angle alpha is.
So I'll use the law of cosines centered at alpha to figure this out.
So the law of cosine says that the side length opposite, squared, should be equal to 6 squared plus 3 squared minus 2 times 6 times 3 times the cosine of alpha.
That seem okay? And apparently we just need to solve this for the cosine of alpha. Well, that's like easy enough to do, right? This is a linear equation.
I'll add this to both sides, and I'll subtract this from both sides. There's more than one way to do this sort of thing, but there's an approach. And I'll even simplify a little bit. 2 times 6 times 3 is 36, I think. So on the left-hand side, I'll now see 36 times the cosine of alpha is equal to 6 squared is 46 plus 9, also known as 45. So apparently the cosine of alpha is 45 over... Oh, Chris, what have you done? I forgot to subtract the 4 squared, but you can't just erase it all. There we go.
36 plus 9 minus 4 squared. Which is 16. And what does that right-hand side simplify to? Is it 29? I feel like it's 29. Okay.
So the cosine of alpha is apparently 29 over 36.
So how could we find out what alpha is?
Use inverse cosine. So alpha is inverse cosine of 29 over 36.
And 29 over 46, there's no simplification to make there. There's no common factor in the numerator and denominator. And if you wanted a decimal approximation, you would now bust out a machine. What's the arc cosine of 29 over 46?
0.634.
Somewhere around 0.634 in radians.
What if we wanted that in degrees?
36.34.
Somewhere around 36.34. So I'll go to 3 digits because that's what I did above. Degrees, specified with little circle.
How do people feel about that? Does it seem okay? Do you think we could do the same thing to figure out the other two angles? Yeah, let's do that.
So to find the cosine of beta, we'll use the law of cosines centered at beta. So that says the side opposite beta, 6 squared, is equal to 4 squared plus 3 squared minus 2 times 4 times 3 times the cosine of beta. If you want to find the angle gamma, you would instead use 3 squared equals 6 squared plus 4 squared minus 2 times 6 times 4 times the cosine of gamma.
What do you think? Do those look like equations that are easy enough to solve? Cool. Find beta. Find gamma.
And as soon as you get an answer, compare it with those around you. Once those around you get answers too. Let's see, at this point I've seen a decent number of people take out their calculators, which presumably you're at the last step of actually computing an inverse cosine once you've taken out a calculator. Let's go see what people got. So for the angle beta, what is beta?
117.3 degrees for 2.05 radians.
Did you say 2.05?
Yeah.
What is it exactly? Both of those are approximate.
Inverse cosine of -11 over 24.
Cool. Notice, since that number inside of the inverse cosine is negative, that will be an angle in quadrant 2. It will be obtuse. But obtuse triangles are just fine. What is the angle gamma?
Inverse cosine of 43 over 48.
Inverse cosine of 43 over,
48.
which is approximately equal to,
About 0.46 radians. Or 26.38.
and as one last little checksum in order to see not if these answers are correct, but to see if they're consistent, what do the angles have to add up to? Let's walk in degrees. 180. I'll use that because I know how to see if a number is close to 180 easier than I know how to see if a number is close to pi. Let's add up these numbers and see what they make. 36.3, 117.3, 26.3, oops. We get 9, 12, plus 7, 9, carry the 1. 1, 2, 3, 4, 5, 6, 7. Is that pretty close to 180? It's only within our rounding error of 180. Since I only did those got those numbers up to the 10th place, I don't trust the result of addition even in the 10th place. Nice. Cool. So there are examples on the next page, which I intend to go through because applications are nice. Otherwise, have questions ready to ask me.
I don't understand why your whole plan is right one half.
Good luck on your practice.
You go from there to there. Oh, okay. So it's 2 times. What's the cosine of pi over 8?
Oh.
Yeah.
get if, like, that angle or the angle whose cosine is 1, so
Yeah.
that would be 0 radians. So it would be like a triangle that's a flat line. That's stupid.
So you'll be in your